Hi and welcome. So this is our exploration of Sylows theorem, supposed to be a W. Exploration of Sylows theorem 9. Okay, and so we've tried a bunch of strategies. The theorem has been the following: suppose we know that order of G equals to p to the alpha times m, where p and m are relatively prime. Does that imply then that there exists some subgroup h of G such that the order of h equals to p to the alpha? Right? That's the question. This is this is what we've been preoccupied with for quite some time now. So we've tried a bunch of strategies, um, most of them not successful. At least we couldn't see how it works out. And last time we tried induction, and we saw that induction seemed to leave a lot of unknowns. So perhaps it's not the way to go. So the natural question that this raises is, well, okay, what can we do? What approaches do we have left? Well, we've been able to make some progress. At least we've been able to say the following, that if the order of G equals to P times M, then we know that there exists some subgroup H of G such that order of H equals to P. Right? So this was a special case. We're able to, this appears like we're able to prove this, or unless there's some error, but it appears to be a solid statement. That in the case where alpha equals to 1, the statement is true. Okay, well, if we can't prove again the whole thing, if it's proving challenging to prove the whole thing, why don't we prove another special case? Maybe that will help us. So, what if, is there any other special case we could think of here that we might be able to prove, although we're kind of having difficulty proving the whole thing? So, well, what about if order of G equals to, the most obvious one just seems to be p squared times m. Let's see what happens if the order of G equals to p squared times m. Can we conclude from there that there exists some h subgroup of G such that order of h equals to p squared? Right? Can we conclude this? Alright. So, I mean, before, how we had proved the special case was just to say that contradiction. Suppose not. Let's try contradiction here. If it doesn't work, then we lose nothing. We could try something else. So, suppose then, suppose instead that the order of G equals to p squared times m, and actually for all h subgroups of G, order of h does not equal to p squared. Right? Suppose this is a true statement, right? So before, what we'd said was that well, now we have an issue, right? The order of if the order of h is not p squared, then we have do we have two? We probably have more possibilities. Um, yeah. Okay. Could we say this then? Either order of h divides p squared, or it doesn't. Right. Hopefully, if we can gain some contradiction here, um, it could help us to figure out. It would help us to conclude the case is true for p squared, and hopefully that will trigger our mind to figure out how to prove the statement in general, if at all it is true. Again, we've just been told, we don't know. So suppose that the order of h divides p squared, right? Either it does or it doesn't. Do you buy this? That either the order of h divides p squared or it doesn't. Well, Well, I mean, even if it doesn't divide p squared, what benefit would that be? Let's try best case scenario. Our dreams come true. Our wet dream is, well, order of h does not divide p squared. That is, let's suppose that order of h actually doesn't divide p squared. So what? Okay. If order of h doesn't divide p squared, can we say that order of h divides m? Okay. Do you buy that? If order of h doesn't divide p squared, can it be, okay, we already said it's not p squared. Can it be p then? No. Can it be 1? No. But if the order of every subgroup must divide the order of the group, then it didn't mean that order of h must divide m. But again, if we're to follow a wet dream here and say, okay, fine, order of h actually divides m, what good is that? Before, the reason that helped us was it was p, so we knew if something is not p, it has to divide m, and which means that the entire group must divide m. But now this is different. Even if order of h divides m, that doesn't seem to be useful to us. What are we going to do with that information? Okay. What if order of h divides p squared? So what? Doesn't that mean that order of h... Ooh, wait a second. If order of h divides p squared, and we're saying that the order of h then must be of the form p, well, unless h is the identity, but so let's say that h is not the identity subgroup. So h is not the identity subgroup. H does not equal the identity. If we suppose that order of h divides p squared, and we're saying that the order of h, oh, actually equals to p. Wow. So, what if the order of h equals to p? So what? How does that guarantee us a subgroup of order p squared? Right. Because order of h, we said, does not equal to p squared. If it divides p and it's not the identity, it must be p, mustn't it? And if it is p, well, so what? So at least this approach of checking divisors may not be of value to us. Or at least we can't see how to make it valuable. So, is there any other way to obtain a contradiction? If we suppose that the order of g equals to p squared times m, and that all subgroups h of g, and that for all subgroups h of g, order of h does not equal to p squared, how could we obtain a contradiction? Or maybe let's put it this way, what sort of contradictions would we like to have? For instance, that there must be something. Let's suppose we found a subgroup. Suppose we found some L subgroup of G such that order of L equals to H squared. Would that, sorry, equals to P squared. Would that be a valid contradiction? Right, since we are supposing that it's not. Well, but if we found a subgroup of order P squared, why did we need to use contradiction? Why didn't we just find the subgroup and then set it, and then just conclude that our statement is true? So, this is proving not to be valuable to us. So, it's time to think up something else. How else can we prove? Um, is there any other contradiction we could obtain that's not kind of obvious? Or maybe if we contradict the fact that the order of g actually is p squared times m, But how do we do that? If there's no subgroup of order p squared, yeah, okay. Is there any other way we can salvage this argument by contradiction? Yeah, it appears to just lead us into more and more mysteries, unclear how it will help us here. So let's try something else instead. Suppose that, let's still try and prove this special case of p squared. So suppose that order of g still equals to p squared times m. P and m are relatively prime. Does this imply that there exists some h such that order of h equals to p squared? Right. So we've tried contradiction and it doesn't seem to be helping us. So let's try something else. What else can we try here? What's so special about a group of order p squared times m? What do we know about it? Maybe we could start listing those things. Well, we know that, can we say that for all subgroups it's possible divisors, the possible subgroups of H have the property that their order is of the form p to some I times L, where L divides M, uh, and I is in between 0 and 2. Okay, those are the, is that something we could say is true about the group of order p squared times m? I mean, given that Lagrange's theorem tells us that the order of every subgroup must divide the order of the group, aren't we saying that it's either, well, it could be just of the form p to the I, in which case couldn't we say that alpha L equals to 1? Or perhaps we have some power of p like p squared and then some divisor. So doesn't this possibility, you're writing that order of h equals to p to the I times L, where L divides M and I is between 0 and 2, isn't that covering all the possible cardinalities that a subgroup can have? Okay, suppose it is. Um, what else can we learn about our group G? If order of G equals to p squared times M, what else can we learn about it? I mean, we're also being told that P and M are relatively prime. Okay, if two things are relatively prime, what does that mean? Can we conclude that P does not divide M? Well, since P is a prime, right? And well, obviously, if M equals to 1, again, that was another special case we looked at. But if M equals to 1, aren't we just done? That is, if we have a group of order G equals P to the alpha times M, where M is 1, isn't G just a subgroup of itself? So haven't we found a subgroup of order P to the alpha? So we're kind of assuming M is not 1, and since P is a prime, can't we say then that if P and M are relatively prime, P doesn't divide M? Can we also say that M doesn't divide P? Right. Suppose that P divided M. Wouldn't that mean that P and M have some factors in common other than 1? Given that P and M are not 1. Okay? Right. So what else can we learn about our group? If we know that a group has order P squared times M, or if we know that P and M are relatively prime, what else can we say? Um, what else can we say? Well, could we say as well that if anything divides P times M, it either divides P or it divides M? Oh, actually, yeah, we looked at that before. Perhaps not. Example would be like 3 and 6, right? So a number like 6, uh, well, yeah, sure. No, but these are not relatively prime. 3 times 2 times 5. A number like 6 divides, if we set m equals to 2 times 5, and we set p equals to 3, a number like a number like 6 is going to divide p times m, but 6 doesn't divide 3, and does 6 divide 2 times 5? Okay, so maybe we can't say that. What else do we know about things that are relatively prime? If two things are relatively prime, then what? Um, Another thing we know is that if we consider z mod mz, say, star, this is the group under multiplication. You get all the elements mod m and figure out those that are relatively prime to m. So can we say this then? P is an element of z mod mz star. Right? Can we say that? So here we're just trying to learn as much as we possibly can about what it means for the order of a group to be p squared times m, what it means for a group to have order p squared. So because the more data we have, hopefully the more our minds will be sparked to come up with an explanation. So if p and m are relatively prime, okay, and p and m are just not 1, so, or at least, yeah, right, we already said that. Can't we say that p is an element of z mod mz star, right? And z mod mz star, we're saying again, is just like, for instance, z mod 6 z star would be, you get all the elements mod 6 and you only pick those that are relatively prime to 6. For instance, 1 is 1 relatively prime to 6. What about uh, 5? Is 5 relatively prime to 6? Is there anything else here? 4 isn't, 5, 3, 2, right. So for example, z mod 5, z mod 6 z star would be just this number here, would be 1 and 5, and it's under multiplication. And indeed, what's 5 times 5? 25. Isn't that 1 mod 6? Okay, so that's the same thing here. We're saying, look, if p and m are relatively prime, can't we say that p is an element of z mod mz star? Can't we also say that m is an element of z mod pz star? Okay, well, why are we saying this? We don't know yet. It's just that it doesn't harm to learn more about our problem. What does it mean to be an element of Z mod MZ star? Well, it means that, well, P can be thought of as an element of a group, uh, P as in the number. So we're treating the powers as groups. Bizarre. The power of P, treating it as a group, the M as well. Okay, that's something we're able to learn. Not sure how it's going to help us, but okay. What else are we able to learn? Can we say that, suppose that we're trying to prove that something has order p to this p squared. What do we know about groups of order p squared? Right. So in the Lagrange video, didn't we prove that if we have a group of order p squared, then it means that it has a subgroup of order p. That is, doesn't it mean that there exists some L subgroup of H such that order of L equals to p? Right. So again, if you're confused about this, just yeah, please do think about it. The claim we seem to have come up with in our series on exploration of Lagrange's theorem was that if order of g equals to p to the alpha, then that implies that there exists some subgroup h of g such that order of h equals to p. Right. See if you buy that statement or not, or can prove it, etc. So if we somehow want to conclude that order of h equals to p squared, well, one way to conclude that is, I mean, not one way to conclude, but if order of h equals to p squared, can't we say that there exists some subgroup L of H such that order of L equals to P. Such that order of L equals to P, okay. So if order of H equals to P squared implies that there is some L such that order of L equals to P. Ooh, what if we proved that there does not exist an L subgroup of H? Alright, we just run out of time. So right now our strategy so far has just been, well, at least for this video, is let's try and learn as much as we possibly can about what it means for the order of G to be equal to P to the alpha times M. Let's also learn as much as we possibly can about what it means for the GCD of P and M to equal to 1. Let's also learn as much as we possibly can about what it means for a group to have order P to the alpha. And in this case, we are proving a special case just when P equals to 2. Okay. And hopefully the ideas used to prove that the theorem is true for P equals to 2 will help us to think about will help us to think about the case when we replace 2 with alpha, when we have P to the alpha times M instead. So yeah, let's learn as much as we possibly can about our theorem here, about the different pieces, and perhaps that will spark our brains to come up with something new. Otherwise, thank you very much for watching this video, and have a relentless week. Bye.